Hey everybody, welcome to video 6C. This is about arcs and chords, and this comes from section 10-3 of your textbook. So we're going to start with vocabulary in this video only, and there's the vocabulary terms in the first two spots here and here are really going to be almost like two terms in one. So I'm going to zoom in a little bit so that we can write as much as we need to in this block. You're going to need to write a little bit small, okay? The first term is when we are talking about an inscribed polygon. And like I said, this is two terms in one. So at the same time we're talking about an inscribed polygon, we're also talking about a circumscribed circle. So that definition, you guys, sorry about that. That definition is a situation whenever a polygon is inside of a circle, and at the same time we can say the polygon is inside the circle. We can also say the circle is around the polygon. Okay, so just go back with me for a second here, and let's think about how we can kind of remember from the way those words are put together. Whenever we're talking about inscribed, we can think about that prefix in, and that means that whatever word comes after, that's the thing on the inside, if you will. For circumscribed, you can think about vocabulary words with that prefix circum, which basically means to go around. That's why we use circumference. And also the vocab word circumnavigate, which means to kind of travel around the globe. Circum means around. Okay, so that's how you can kind of think about the prefixes and what the definition should be. Just a little bit of literacy help for that. So as we're thinking about what the diagram looks like when a polygon is inside of a circle, I'm going to take an example here of, let's say, an inscribed pentagon. And so when you have an inscribed pentagon, we're going to start with a circle, and the pentagon would be on the inside of the circle, meaning that all the corners of the pentagon, if you will, are right on the circle itself. And remember, we can state this in two ways. We can say it's an inscribed pentagon, and we can also say that it is an example of a circle that is circumscribed around a pentagon. Pentagon. Okay, so that's our first definition. What we're going to do is we're going to basically take the opposite of that for our second definition. So this time, instead of inscribing the polygon, we are going to inscribe the circle. So our second definition here is when we have an inscribed circle and at the same time we're inscribing the circle, the opposite of what we had before, we are going to have a circumscribed polygon this time. Definition shouldn't come as a shock to you. That's the situation that instead of the polygon being inside of the circle, it's the other way around. It's when a circle is inside of a polygon. And again, two-sided definition there. It's also, we could say, when a polygon is around a circle. So the definition, or excuse me, the diagram that goes with that would be a situation where, let's say we had a triangle and then a circle inside of it. This would be an example of an inscribed circle. At the same time, it's also an example of a triangle circumscribed around a circle. So keep in mind those definitions, okay, can go either direction. Make sure that you know them in both ways. And we'll go back and we'll just highlight those prefixes again on the second definition set there. Whenever we're talking about an inscribed circle, that's when the circle is on the inside. And whenever we're talking about a circumscribed polygon, that's when the polygon is around the figure, the circle. Okay? All right, so let's keep going. The next three definitions that we're going to have in this video are just talking about more, actually not definitions, but theorems. So you can put in Theorem 10.2, Theorem 10.3, and Theorem 10.4. So I just want to make sure you guys realize that when we're talking about these theorem names, you do not need to know them by name. You just really need to know how to use them in the upcoming examples in the next video. So don't really stress about memorizing the name 10.2, etc. But you do need to know what they mean, okay? So anytime we're having a theorem, remember we've got an if part and a then part. It's an if-then conditional statement. So we can go ahead and just write that actually in each box, and we'll fill in as we go here. For Theorem 10.2, when we're looking at our if and then our then, the if part is when we start with two chords. And remember, a chord is a segment that joins 2 points on the circle from the last vocab video we had. If two chords are congruent, then what we can conclude is that their corresponding arcs are also congruent. And just know actually that this theorem goes both directions. So if we know chords are congruent, then we know the arcs are congruent. If we know the arcs are congruent, then the chords are congruent as well. As far as a diagram that goes with that, there isn't really a great way to visualize it. So I just kind of coded it like this. If you start with a circle with two chords and you have congruent markings on those chords, then you can say that that means that in that same circle, the arcs that are cut off also have congruent arcs there, okay? Again, arcs being congruent means that the measures of those arcs are equal. So that's what we're looking at for Theorem 10.2. The next theorem, 10.3, the if and the then on that one, are still talking about chords, okay? But specifically we're talking about the situation if we know that a radius, or actually a diameter too, that is drawn perpendicular to a chord, then that means it bisects the chord. Ooh, I can't spell. Hang on. Let's try that again. It bisects. So remember, that means it cuts it into two equal halves. And that's a pretty easy picture for us to draw here. So in that case, we have a circle we have a chord of some kind and we have a center. And if the radius goes to the chord at a 90-degree angle, then what we can assume is that on that diagram, the other two pieces of the chord that it's cut into are congruent. So now our last definition for this video is Theorem 10.4. And Theorem 10.4 talks about chords and their distance from the center of a circle. So we're going to start with if two chords are equidistant, the same distance away, in other words, from the center of a circle. And just so you know, that is always measured at a 90-degree angle, distance from a line to a point. Then what we can conclude is that the chords are congruent, that they're the same length. There's not really a picture that goes with that, but we'll talk about that in an example in a future video. So there's your vocab.